Hi everyone, Dr. Burns here with our second lesson in Chapter 9, Chemical Reactions in Aqueous Solutions. In this lesson we're going to be learning about two new types of reactions, acid-base reactions and oxidation-reduction reactions. We've talked a little bit about acids and bases in our previous lesson, but just to review, acids can either be strong or weak. A strong acid is a strong electrolyte, meaning that it dissociates completely in water. And specifically, the 7 strong acids that we have to memorize are molecular compounds. So when they are put into water, they ionize. We don't typically break bonds when we put molecular compounds into solution. However, when it's an acid, specifically a strong acid, we do break that bond. And that's how we're able to form the ion. So we have a list here of our strong acids that we were told to memorize in our previous lessons. We also have a list of strong bases, which we defined as hydroxide ion containing compounds that are paired up with group 1 and group 2 metals. So we have lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium. Strong bases are also strong electrolytes, meaning they dissociate completely. These are ionic compounds because they have a hydroxide ion and are made up of a group 1 or 2 metal. Therefore, they dissociate into their specific ions. They don't react with water in any way. A weak acid is a weak electrolyte, meaning it does not dissociate completely in water. It only dissociates partially. If a compound is defined as an acid, and it's not one of the 7 strong acids that we've learned about in the past, then it is considered a weak acid. We only have 2 types of acids, strong and weak. So, if it's not one of the 7, it is a weak acid, and there are more weak acids than strong acids. We can further define acids and bases. We have 2 different definitions for them. The first is the Arrhenius definition of acids and bases. And this is what we were discussing previously, where an Arrhenius acid is one that ionizes in water to produce hydrogen ions, H+. So this is what we saw in our previous lesson, where we saw our strong acid dissociating into its individual ions through ionization. For the Arrhenius base, it is one that dissociates in water to produce OH ions. Again, this is what we previously discussed, where we said acids have a hydrogen and bases have an OH. Another definition of acids and bases is the Bronsted definition. And this specifically has to do with a proton. A Bronsted acid is a proton donor, meaning it will give away a proton. A Bronsted base is a proton acceptor. So the acid gives up the proton and the base will accept it. In these definitions, a proton refers to a hydrogen atom that has lost its electron, which is also known as the hydrogen ion. So remember, hydrogen ion is H+. Hydrogen only has 1 proton and 1 electron, so if we form an ion of hydrogen, it has lost all of its electrons. It's lost its only 1 electron. So all that ion is made up of is a proton. So that's why we say we can donate and accept a proton through the Bronsted definitions of acids and bases. Here's an example of a Bronsted acid and Bronsted base in action. So we have NH3 ammonia reacting with water H2O, creating NH4+ and OH-. Here, NH3 is acting as the Bronsted base, because it is transforming on the reactant side from NH3 into NH4. So it has gained a hydrogen ion, I should be specific. So it accepts the proton in order to become NH4. So we say that NH3 is the Bronsted base in this reaction. Water is then the Bronsted acid because it had to give up one of its protons it gave up its H plus in order to become OH minus. Therefore, since water donated a proton, H plus, it is then the Bronsted acid. You'll notice here that because we are switching protons around, we're moving those hydrogen ions, our charges are changing from our reactant side to our product side. So we see the NH3 becoming more positive, and we see the H2O becoming more negative. But if we look at both sides of the equation, our reactant side has a charge of 0, and so does our product side. So we have a plus and a minus, which cancel out to 0. So just because we're moving around a proton, we need to keep in mind that that proton has a charge, so it's going to change the charge. If it's being removed, then the charge becomes more negative, and if it's being added on, the charge becomes more positive. Bronsted acids donate protons to water to form the hydronium ion. So in the case here where we have HF, HF is going to be our Bronsted acid, meaning that water is going to be the Bronsted base. So this hydrogen from HF is going to be donated to water. So water with an additional hydrogen is called a hydronium ion. So now we have oxygen with 3 hydrogens on it and an overall charge of positive. So we can refer to the moving of a proton or the changing of the charge in 3 different ways. We can say that we've donated a hydrogen ion, we say that we've donated or accepted a proton, or that we've created the hydronium ion. The hydronium ion isn't just another way of saying hydrogen ion and proton. They all refer to the same aqueous species in the reaction. So let's do some practice with this and moving around our protons using our Bronsted acid and base definition. Our first problem here wants us to predict the products of the reaction below. So we have HNO3 reacting with water. Well, we know that HNO3 is nitric acid. Since HNO3 is an acid, based off of the definition of Bronsted acids and bases, it is going to donate a proton. That proton is going to be the hydrogen, so that hydrogen is going to be moved onto the water. When we add an additional proton onto water, that's when we get the hydronium ion, H3O+. I account for the charge because the additional proton is bringing that plus charge. We've increased the number of protons, so we have to, our molecule becomes more positive. When we remove the hydrogen from HNO3 from nitric acid, it really is just like we got rid of it. So we have NO3. But the charge on that now has to be negative because we removed a proton. We only removed the proton, so the charge now becomes more negative. There's now an additional electron around, making that overall compound negative. So our final products of this are the hydronium ion and the nitrate ion, which is a polyatomic ion. The next problem wants us to identify each of the following species as either a Bronsted acid, a Bronsted base, or both. There are compounds that can act as both an acid or a base. The biggest example of that is water. We've already seen 2 examples where water could accept protons as well as give them away. So some species can act as both an acid and a base. So let's look at these examples. Our first one is HI, hydroiodic acid. Well, the name tells us that it's an acid, but let's look at why. It has a hydrogen to give away. Therefore, it can donate that hydrogen. If it has a hydrogen to donate, it means it's an acid. Now, it cannot accept a hydrogen because it does not have anywhere for that hydrogen to be put onto. If we look at our structure of hydroiodic acid, we know that iodine has 3 lone pairs and only prefers to make 1 bond. So there's no additional place for that hydrogen to go if we were to accept it. So hydroiodic acid would not act as a base. Next up, we have C2H3O2-. This is the acetate ion. Acetate, as it's shown here, does not have a hydrogen that can be given away. The hydrogens that are in the middle here, when we see hydrogen in the middle of the formula, it means that they cannot be given away. Here we have hydrogen out in front. In other examples, we've seen hydrogen out in front, okay? And we may see it at the end as well. But if it's wrapped up in the middle of the formula, that's our way of showing that those hydrogens cannot be given away. So this will not act as an acid. Now, can it accept a proton? Well, it has a charge. So it has a negative charge, meaning it could be willing to accept a hydrogen to balance out that charge and become neutral. So because it is able to accept a charge, a positive charge, it can then become a base. So it can have a proton donated to it. So if we were to add a proton to this, it would be H C2H3O2. And now we have a charge of neutral because we've added a proton on to balance out that negative charge. Next up, we have NH4 plus. That plus charge is what's going to indicate to us that we have an additional proton that is on our central atom of nitrogen. Okay, so we have a plus charge overall for this compound. We know that nitrogen prefers to have 3 bonds and 1 lone pair. Therefore, NH4 plus is more likely to give away one of these protons and keep the 2 electrons that are in that bond as its own lone pair. So we're going to see this hydrogen come off and be donated to other compounds. So if the proton is being donated, then NH4 plus is going to act as an acid. When it gives it away, it becomes NH3, which is neutral. Okay, our last example is HPO4 2 minus. Now we have a charge here of 2 minus, as well as a hydrogen out in front of that formula. If we see a hydrogen out in front, that hydrogen is able to be given away or donated to other compounds. So we could see this as acting as an acid. If we give away that hydrogen, our compound becomes PO4 3 minus. The charge on this compound also suggests that this could act as a base because we want to decrease our negative charge and try to get to a neutral charge. So HPO4 2 minus can also act as a base. So it can accept a hydrogen right? That's the definition of a base, is of a proton acceptor. So it's going to accept a hydrogen, and what that's going to do is make the formula H2PO4, and that's going to decrease our charge to a -1. So we're getting closer to a neutral molecule. It can act as a base again. This compound can then act as a base and accept another hydrogen and become H3PO4 with a charge of 0. It's neutral, which is where we want to be. So HPO4 2 minus can act as both an acid and a base, based off of the definition of a Bronsted acid and a Bronsted base. Let's do some additional practice. This one comes from your ALEKS homework. Determine all chemical species present when the following acids are dissolved in solution. So here we're given the formulas of the acids, as well as if they are a strong acid or a weak acid. We know that if it's strong, it's going to dissociate into ions, and that will be the only species in solution for these specific acids. If it's weak, we see partial dissociation. So we see both ions and compound in solution. So let's start with our first example. HBrO3 is defined as a strong acid. So these are in water, so we already know that one of the main species in the solution is always going to be water. There's always going to be H2O. If we were to take our microscopes that can look at individual atoms, which obviously there isn't, so it's a magical microscope, we would see individual molecules of water. And since this example, HBrO3, is defined as a strong acid, we would also see H+ ions as well as BrO3 ions. Since it's strong, it fully ionizes, and we break this off to have our hydrogen ions and our anions in solution. And those would be the three main species present in the solution. Our next example is a weak acid. So we know with weak acids we see partial dissociation into ions, but we also see full compounds or full molecules present in the solution. So for H3PO4, we would see predominantly H3PO4 molecules still intact in solution, but we would also see some H+ ions as well as PO4 3- ions. We have to account for the 3 here on the hydrogen. That 3 is coming from our phosphate ion. Phosphate is one of our polyatomic ions, which we know has a charge of 3-, so you have to account for that charge properly. Okay, what I want you to do for the last 2 problems here is write out the chemical species that are present in solution for these last 2 acids. H2S is defined as a weak acid. So similar to our previous example, we would see H2S molecules in solution, as well as some hydrogen ions and sulfide ions in solution. And our last example is hydrobromic acid, which is one of our 7 strong acids. So just like our first example, if it's a strong acid, we would only see hydrogen ions and bromide ions in solution with water. Okay, we can define acids based on the number of protons that they can give away in solution. So we first have a monoprotic acid, which has 1 proton to donate. Mono meaning 1, protic meaning proton. Hydrochloric acid is an example of a monoprotic acid. HCl only has 1 hydrogen to give away. So we only give away 1 hydrogen ion, and therefore once that's done, I have no more hydrogen ions to give away. So only 1 proton that can be donated from a monoprotic acid. Another type of acid is a polyprotic acid, and these have more than 1 acidic hydrogen atom attached to them, so they can give away, or I should say donate, more than 1 hydrogen. So acidic hydrogens are protons that can be given away, hydrogens that can be given away. Sulfuric acid, H2SO4, is an example of a diprotic acid. Di meaning 2, we get that from the 2 on the hydrogen of sulfuric acid. So there are 2 acidic hydrogen atoms in sulfuric acid. So polyprotic acids are going to lose their protons in a stepwise fashion. They don't just give away both of their protons in one step. So with sulfuric acid, we see H2SO4 under its first ionization giving away just 1 hydrogen. The product of that is now the hydrogen ion as well as HSO4 minus. The hydrogen of HSO4 minus is still acidic, it's still able to be donated, but that will happen in a second process. So our second process here starts with HSO4 minus, and now that second hydrogen can be given away or donated, and we get hydrogen ion out, as well as the sulfate ion. Our first step here with sulfuric acid is strong, so we see full ionization of that hydrogen ion and HSO4. However, the second process, where we start with HSO4 minus, this is now a weak acid. So if we have a polyprotic acid that starts off as a strong acid, which only applies to sulfuric acid is our only polyprotic acid that's strong. Okay, the acid that we start with in the second ionization is then a weak acid. It's less likely to give away that hydrogen. We follow our weak acid definition. When acids and bases are mixed together, the reaction that occurs is called a neutralization reaction. A neutralization reaction is a reaction between an acid and a base. Generally, a neutralization reaction produces water and a salt as the products. So in our example here, we have hydrochloric acid reacting with sodium hydroxide. Hydrochloric acid is our acid, sodium hydroxide is our base, and what they do is their product is now water and a salt, sodium chloride. The net ionic equation of many acid and base reactions is H plus OH minus reacts to create H2O liquid. Neutralization reactions are a type of double replacement reaction. So if you recall from our previous lesson where we learned about precipitation reactions, which were our type of double displacement reactions, we saw that the cations replaced their anions, or they swapped their anions with the other reactant. And that's exactly what's going on here. So we see Cl and OH switching places. So Na now goes with Cl, and that's how we get NaCl. And the H plus and the OH minus come together to create water. So this is an example of where it might be easier to write water as HOH, so that you can see that it is made up of the hydrogen ion and the hydroxide ion coming together and forming water. You'll find this specifically useful when we start to balance these types of reactions. So because this is a double replacement reaction, and we have H plus ions floating around and Cl minus ions floating around, as well as NaOHs, Na pluses, and OH minuses floating around, we can write ionic and net ionic equations for these reactions, just like we did with precipitation reactions. Here, the aqueous product is still going to be our spectator ions, but instead of forming a precipitate, we're forming liquid water. So our rule with ionic equations and net ionic equations is whatever has an AQ notation is written as its ions. Water does not have an AQ on it, therefore it would remain as H2O in the ionic equation, similar to how our precipitate stays as a solid. Everything else has AQ, so it's represented as its ions, meaning the net ionic equation would be the formation of the liquid water, H plus, OH minus, creating H2O liquid. This is why we need to fully understand the difference between the notation AQ and the notation L. L refers to a pure liquid. And we said the only pure liquid that we're going to be looking at in this class specifically is going to be water. Everything else is going to be dissolved in water and get an AQ notation. Okay. So because these are double replacement reactions, we are fully able to predict their products in the same way we did with precipitation reactions. So to practice that, let's write out the balanced chemical equation for the acid-base reaction between a solution of barium hydroxide being neutralized with a solution of nitric acid. Once we're done with that, we'll write the net ionic equation. So we're going to start this out just like any other problem where we're predicting the products. We have barium hydroxide and nitric acid, and these are both solutions. So we know barium hydroxide is BaOH2. Barium is a group 2 metal, so it's going to have a +2 charge, and this gets an AQ notation. We add to that nitric acid, which is one of our strong acids, HNO3, with AQ notation. So we can write these as their individual ions, Ba2 plus, OH minus, H plus, NO3 minus, and we can do our swap. So we have H plus going with OH minus, we have NO3 going with Ba2 plus. So this creates the product of HOH, again that's water, and then we get, which has an L, then we get BaNO3 2 to account for the charges. And this would be AQ because we know nitrates are fully soluble in water. In order to balance this, we would just need a 2 out in front of our HNO3 and a 2 in front of our water. Again, when it comes to balancing, you will find it significantly easier if you see the H and the OH as separate entities because we have an OH here. Sometimes having the H's in separate spots in the reactant side gets tricky with the balancing. So if you remember to keep your polyatomic ions together, which in this case would be the OH as well as the NO3, it makes balancing go a lot easier. Okay, so to write the net ionic equation, we are going to see what isn't in aqueous form, which is our water. So in order to form water, we have H2O. We had to bring together H plus ions, which were aqueous, and OH minus ions, which were aqueous. Oops, ran out of room there. Let's move this over. In our balanced equation, we had 2 waters, 2 hydroxides, and 2 H pluses. However, we have to remember that if we're writing balanced equations, we have to show the simplest whole numbers. So we would divide this whole thing by 2, and we would get H plus OH minus creates H2O. I'm forgetting my notation, AQ on both of these. So there's our net ionic equation, which follows our rule from our previous slide that the net ionic equation for many of these acid-base reactions is H plus OH minus goes to H2O. So let's continue practicing with this. For the following equations, balance them and write the ionic and net ionic equations for both of them. We know what the outcome of this reaction is going to be. We know at least one reactant is always going to be H2O because we have an acid and a base. So that leaves us our 2 other ions that are going to mix together to form our salt. So KC2H3O2, acetate ion has a -1 charge, potassium ion has a +1 charge, so they're just in equal but opposite charges, so 1-to-1 ratio, and that gets an AQ. And for our final reaction, we have Na2CO3. We have to remember that carbonate has a 2- charge on it, so when it mixes with sodium, which has a 1+ charge, it is going to, we need 2 sodiums to balance out that carbonate. But this is aqueous because group 1 compounds are soluble in water. Okay, so what I want you to do now is, now that we've solved these 2 equations, balance them, and then write out their ionic and net ionic equations. Since these are both acid and base reactions, acid-base neutralization reactions, we already know the net ionic equation. Since we get water out in both of these, we know it's going to be H plus OH minus becomes H2O. Same goes for down here. Okay, that's an L. Okay, I draw my L's as curvy L's so that you can easily tell that they're an L and not a 1. Okay, so we know our net ionic equation. That's a given for these types of reactions. So all we have to do is balance our chemical equations and then write out the net or the total ionic equation. So our first one is completely balanced, everything's in 1-to-1. Our second one, we needed 2 in front of the NaOH, 2 in front of our water, there we go. If you had trouble balancing these, please go back and review our video on balancing chemical equations. You're going to need to have that completely mastered if you want to fully understand this lesson and the following lessons. Okay, so our ionic equation for this first one is going to be H+. I should move this over so I have enough room. Plus my acetate ion. Plus potassium ion. And hydroxide ion. We create water, but water does not have AQ as its notation. It is a full molecule, so we keep it together in the ionic. So we keep that as is. It does not have AQ notation, it has L notation because it's a pure liquid. If we were to look at water in our water bottles, it would be H bonded to an O bonded to an H. We would not have any ions there. And then we have K, potassium again, and we have acetate ion as well. So we can see here that our spectator ions are the potassium and the acetate, which is our aqueous product, which correlates to our net ionic equation of H plus OH minus creates water. Okay, and our last one, all we have to make sure we keep track of is our balancing in our ionic equation. So we have 2 H pluses that are aqueous, and 1 carbonate ion with a 2 minus charge that's aqueous. Then we have 2 sodiums and 2 hydroxides. Oops, that should be an OH. OH minus, there we go. Again, water is our product that's going to stay together. So we're going to keep that as is and put our 2 out in front. And then we have 2 sodiums again and a carbonate. And we see our spectator ions are sodium and carbonate because they are the same on both sides of the equation and they are our aqueous product. And when we move from our ionic to our net ionic equation, we want to make sure we divide by 2 so that we have the simplest whole number ratio between all of our reactants and products in our balanced chemical equation. Okay, so we're going to move on now to our next type of chemical reaction. And these are called oxidation-reduction reactions. An oxidation reduction, also known as a redox reaction, is a chemical reaction in which electrons are transferred from one reactant to another. So oxidation is the loss of electrons, and reduction is the gain of electrons. So let's look at an example of a redox reaction. Here I have zinc solid reacting with copper ions that are in solution. In my image here, I literally have a piece of zinc metal that I'm putting into a solution that has copper ions in it. Copper ions, fun fact, are blue when they're in solution. So if you ever see a blue solution in chemistry lab, it's probably a copper solution because they turn blue. Okay, so what's happening is the zinc and the copper are essentially changing places, right? Copper's a metal and zinc's a metal. What's going on is that zinc metal is made up of individual zinc atoms, and the copper ions want to become a solid. So they're changing places, and in order to do that, they are exchanging electrons. So we start with copper ions and zinc solid, and what happens is because they have a difference of 2 electrons, zinc says, I'll give you 2 of my electrons, and I'll become zinc 2+, right? A loss of 2 electrons makes you a cation with a 2+ charge. And that means if I give you those 2 extra electrons, copper, you'll become copper solid. And over time, what happens is with each zinc that goes into solution and a copper comes out, we keep seeing that transfer of electrons, right? We see it happening up here as well as down here. They're literally just giving them away, transferring them from one metal to another. And it ends up where our zinc solid is now copper solid and a bunch of zinc ions. So they literally changed places. So through the exchange of electrons, we went from zinc solid to zinc ions that are aqueous in solution. And in turn, the copper ions that were in solution became copper solid. So they changed phase. And the only way they can do that is if they transferred electrons. So, again, to reiterate, zinc, when it's a solid metal, it has all of its protons and its electrons. So it has a 0 for a charge, right? It's neutral. Zinc would rather be in solution, and copper would rather be a solid. So what happens is zinc says, I'll give you 2 of my electrons, so it loses 2 electrons and becomes, here's that line, becomes zinc 2+. The electrons have to go somewhere. So the copper, which has a 2+ charge, is like, I'm missing 2 electrons. I'll take those 2 electrons that you're giving away, and I'll become copper solid. Because if we add 2 electrons to a 2+ cation, it becomes neutral with a charge of 0. And any metal with a charge of 0 is a solid. Okay, so we see copper ions that were in solution becoming solid, and we see zinc solid turning into copper ions in solution. So what's happening here is we are exchanging electrons. Oxidation is the loss of electrons, and reduction is the gain of electrons. So since zinc lost electrons, it gave them away, it lost 2 electrons, it is being oxidized. And since copper accepted those electrons, it gained additional electrons, it is being reduced. So oxidation and reduction reactions, again, are the exchange of electrons between our 2 reactants. And oxidation is the loss of electrons, and reduction is the gain of electrons. A redox reaction overall is the sum of an oxidation half reaction and a reduction half reaction. So half reactions are just showing for that specific metal or that specific compound what is happening to the electrons. So it's really just showing half of the reaction that's going on. So in our zinc and copper example that we just looked at, we said that zinc was being oxidized and copper was being reduced. So the oxidation half reaction shows that zinc solid turns into zinc ions, and because it lost 2 electrons, the product of that oxidation is the zinc ions and the 2 electrons that it lost. It decomposed into an ion and 2 electrons. The reduction half reaction shows that copper gains 2 electrons, so if it's gaining, those electrons are going to be on the reactant side because it's part of that reaction. They need to be there for the reaction to be complete. So it gains 2 electrons and turns into copper solid. These are half reactions because they're only showing half of the reactants and what's happening to that specific reactant. So we can then add those 2 half reactions together to get the overall redox reaction, which is copper aqueous and zinc solid turns into zinc aqueous and copper solid, which is the example we saw on the previous slide. When we do this, we see that those electrons that are being transferred cancel out, just like our ionic equations. Anything that's similar on both sides or anything that's the same on both sides of those arrows are going to cancel out. Since the 2 electrons from the zinc had to go somewhere, they can't just float around in solution, right? We can't have just rogue electrons everywhere. So they need to go to the copper. So they should be canceling out in the overall reaction. We would not have any extra electrons left over in our reactions. Okay, we have some special terms for what's doing the oxidation and what's doing the reaction. So zinc, which was being oxidized in our reaction, functions as a reducing agent because it provides the electrons for copper. So it allows the reduction to happen. So whatever's being oxidized is then the reducing agent. It provides the electrons for the reduction to happen. Copper then functions as the oxidizing agent. So copper was being reduced. So it functions as the oxidizing agent because it effectively removes the electrons from zinc. So it accepted those electrons. It gave the electrons a place to go, allowing the oxidation to occur, allowing zinc to lose its electrons. So whatever is being reduced is the oxidizing agent. And that is always what's going to happen. If it's being oxidized, it is the reducing agent. If it's being reduced, it is the oxidizing agent. We have some mnemonic devices that we can use to remember how the electrons are being transferred in oxidation reduction reactions or redox reactions. The first one is oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. So this one, oil rig, is talking specifically about the electrons. It doesn't have a term in there that specifically says electrons. I personally like oil rig over the other one, but whatever one speaks to you more that allows you to remember this, use it, okay? So the other mnemonic device is Leo the lion goes grr. So we have Leo, L-E-O, lose electrons oxidation. And then we have grr, gain electrons reduction. So Leo the lion goes grr is a little bit longer, but at least it reminds you that it's the transfer of electrons in oxidation and reduction. So whichever one you choose to use, it works the same way. They're telling you the same thing. Oil rig or Leo the lion goes grr. It just depends on what makes more sense to you. So let's practice. So for the balanced redox reactions, I'm going to change this. So feel free to change this in your own lecture notepad. I don't want to write the half reactions. We'll get to that later in this. And we're not going to identify I guess we can identify the oxidation or reducing agents. But what I want us to do first is just identify what is being oxidized and reduced. Okay, so I'll put our little mnemonic devices up here. Oil and rig, and Leo and grr. Okay, so we're not going to write the half reactions just yet. We'll do that more so in the later half of this lesson when we talk about overall reactions. So let's just not write the half reactions just yet. So for these balanced reactions below, identify what is being oxidized and reduced, and then identify the oxidizing and reducing agents. So the first thing you're going to want to do when you're looking at these is think about the charges, right? The charges are going to tell us how those charges are changing, where the electrons are going. So we need to look at the charges of everything in these compounds. So iron by itself is a metal, so it has a charge of 0, right? We know that. When we just see iron metal, it's coming straight off of the periodic table. It hasn't lost any of its electrons. There's no charge on there. Therefore, it has a charge of 0. Oxygen gas is also the elemental form of oxygen, so it also does not have a charge. There's no ion there, so it also has a charge of 0. On our product side, we have iron 3 oxide, and that's an ionic compound. It's made up of a metal and a nonmetal. So we know we can separate this guy into its 2 charges. So we do a little reverse crisscross. The 3 came from the iron, the 2 came from the oxygen. So we get Fe 3 plus O 2 minus. Okay, so now we want to look at how those charges are changing. Well, to go from iron to iron 3 plus, what happened to my electrons? Well, if I became a cation, I had to lose some of my electrons, right? I lost electrons in order to turn into a cation. So how many electrons did I lose? Well, I went from a 0 charge to a 3 plus charge, so I should have lost 3 electrons. For oxygen now, oxygen went from 0 and it turned into oxygen with a 2 minus charge. In order to go from a neutral charge to a 2 minus charge, in order for it to get more negative, we had to add on more electrons, right? An anion is the gain of electrons. If I have more electrons than protons, it's more negative. So this one gained electrons. So oxidation is loss, reduction is gain, or lose electrons oxidation, gain electrons reduction. Well, lost electrons, oxidation, iron lost electrons, so Fe lost electrons, therefore it's being oxidized. Oxygen gained electrons, therefore gain electrons reduction, it's being reduced. We next want to determine what the oxidizing and reducing agents are. Well, we said whatever is being oxidized is the reducing agent. So iron is the reducing agent. And whatever is being reduced is the oxidizing agent. So they're just opposites. You just got to remember that they're opposites. Whatever is being oxidized is allowing the reduction to happen, therefore it's the reducing agent. Whatever's being reduced is allowing the oxidation to happen, so it's the oxidizing agent. Our next example is then Cl2 reacting with sodium bromide, creating sodium chloride and bromine. Well, we have to look at our charges first. So we have chlorine gas, Cl2, and since that's its elemental form of chlorine, it has a charge of 0. The same goes for Br2, it has a charge of 0. NaBr and NaCl are both ionic compounds, so they're made up of ions. So we know Na has a positive 1 charge, and Br has a -1 charge. On the product side, Na again has a +1 charge, and Cl- has a -1 charge. So, sodium did not change on either side of the arrow. Okay, its charge did not change; it remained as sodium plus. So we are going to define Na plus as a spectator ion. It follows the same definition of spectator ions in our previous lesson, where it did not change from reactant to product side. It's the same on both reactant and product sides, so it is not going to be oxidized, it's not going to be reduced, it is just a spectator. So let's look at chlorine and bromine to see which one is being oxidized and which one is being reduced. We have Cl2 that turns into Cl-. Well, if I went from a neutral charge of 0 to a -1 charge, I had to gain electrons in order to do that, right? I had to add on some electrons. For balancing, this would be a 2, so that would end up being 2 electrons. Don't worry about balancing that, and right now we'll talk about that later. So chlorine gained electrons. If we look at bromine, it went from Br minus to Br2. Again, we'll just balance that for fun, okay? Br2 has a 0 charge, Br minus has a -1 charge. So in order to go from a negative charge to a more positive charge, we had to lose electrons, right? I had to give away electrons in order to get back to neutral. So I lost some electrons there. So, lose electrons, oxidation, lost electrons, which means Br lost electrons, so it's being oxidized. Chlorine gained electrons, gain electrons reduction. So Cl gained electrons, so it's being reduced. If it's being reduced, it is then the oxidizing agent. And if it's being oxidized, it is then the reducing agent. To clarify one point specifically for your ALEKS homework, I do believe that they ask you, when they ask you to identify the oxidizing agent and the reducing agent, since Br is what's being oxidized and therefore is the reducing agent, the entire the entire compound of NaBr would be considered the reducing agent. So they're looking for the full formula of where that came from. So since Br minus came from NaBr, the reducing agent would be NaBr. Other textbooks, other places, they say the reducing agent could just be the ion that's changing, and we don't need to worry about the spectator ion, but I do believe your ALEKS homework does want you to put the entire compound formula in when it asks you for the reducing agent and the oxidizing agent. So, for example, chloride, you would actually put in Cl2 as the oxidizing agent, not just Cl. So, keep that in mind when you're being asked on your homework for the oxidizing and reducing agents. They want the full compound, not just the ion that's changing. Okay, so we can quantitatively, so using numbers, determine what is being oxidized and reduced in any chemical reaction. Okay, we can use numbers to determine this, so we can physically see through the numbers how is the charge changing to determine how the electrons are moving around. And this is referred to as the oxidation number. The oxidation number is the charge of an atom, or charge that the atom would have if electrons were transferred completely. So oxidation number is kind of just a little fun like Sudoku type game I like to compare it to, because you're just kind of filling in numbers. But it's all whole numbers, there's no halves or anything like that, it's just counting. So we have the example here, which we already kind of have been looking at, honestly, since we've been doing ionic compounds. So we have H2 reacting with F2, creating HF. This is exactly how we started our previous problems. I said, okay, H2 is elemental, right? If it's elemental, it's coming right off a periodic table, it has a charge of 0. That charge can be referred to as the oxidation number. So H2 had a charge of 0, its oxidation number is 0. Okay, so we've already kind of been doing oxidation numbers. F2 as well is elemental fluorine. Elemental fluorine comes right off the periodic table. It hasn't lost any electrons, gained any electrons, so it has a charge of 0, meaning its oxidation number is 0. Again, in our previous examples, I then said, well, let's look at our products. Okay, our product is an ionic compound. In this case, it's a strong or an acid, so it can separate into its 2 individual ions. So if we were to look at the charge of those, well, we know F has a charge of -1, from the periodic table, and H has a charge of +1 in order to balance out that fluorine. So again, it's just relating to our charges of what we've done when we've quantified ionic substances. Okay, so in HF, the oxidation number of hydrogen is now +1, and the oxidation number of fluorine is now -1. We can then use that in the same way we did in our previous examples to determine what's being oxidized and what's being reduced. So hydrogen went from 0 to +1. If we went from a charge of 0 to a +1 charge, we had to lose electrons, right? If we become a cation, we lose electrons. That's our definition of cation. If I got a +1 charge, I lost electrons. I have more protons than I do electrons now. For fluorine, I went from 0 to -1. If I went to a more negative charge, I gained electrons. Okay, this is exactly what we did in our previous examples. So we already got a head start on oxidation numbers. If we gained electrons, that means this is reduction. And if we lost electrons, this is oxidation. Okay, so we'll practice this a little bit more. The oxidation number is sometimes referred to as the oxidation state, okay? And these oxidation states have individual numbers for the specific elements, as well as an overall contribution to the molecule at hand, which we'll look at through our examples today. So we do have some guidelines for assigning oxidation numbers. So these are really good rules and guidelines to follow when determining oxidation numbers in compounds that are a little bit more complex than our basic ionic compounds, or if we wanted to find the individual oxidations of all elements, say like if we had an ionic compound with a polyatomic ion, where I have multiple elements that are both ionic or metals and nonmetals. So the first one is the one that we've been saying all along. The oxidation number of an element in its elemental form is 0. The charge of an element in its elemental form is 0. So that corresponds to its oxidation number. The oxidation number in any chemical species must sum to the overall charge of that species. So, if the molecule overall has a neutral charge of 0, then all of the oxidation numbers, when added up, have to also equal 0. If there's a charge on that compound, so if there's an ion that's present, all of the oxidation numbers have to add up to that charge, positive or negative. You have to take the sign into account. And the oxidation number of a monoatomic ion is then equal to that charge of that ion. So if I have O2-, then my oxygen has an oxidation number of 2-, because my oxidation numbers have to add up to that whole, my oxidation numbers of my elements have to add up to the overall charge. There's only one element, and it has a charge, then my oxidation number of that one element is that charge. For the summing to 0 example, we had HF. We said H had a +1, F had a -1. HF has an overall charge of 0, so +1 and -1 equal out to 0. And we'll look at this one more specifically through our examples. It's just a little bit easier to explain through examples. Our final guideline is to know the elements that nearly always have the same oxidation number. So there are some elements on our periodic table that have only one oxidation number, or most of the time have the same oxidation number. And those elements are in this table. There are some exceptions for some of these, but most of the time they follow these rules. So fluorine will always have an oxidation number of -1. There are no exceptions to that. If you see fluorine, it'll have an oxidation number of -1. A group 1 or 2 metal will always have an oxidation number of +1 or +2, respectively. So group 1 will have an oxidation number of +1, and group 2 will have an oxidation number of +2. there are no exceptions to that rule either. So if you see sodium, you know its oxidation number is +1. If you see magnesium, you know its oxidation number is +2. Okay? So, no exceptions to that. Hydrogen will always have an oxidation number of +1. The only exception to that is if it's with a group 1 or group 2 metal and form a metal hydride. So if we have LiH or CaH2, well then our group 1 and 2 metal oxidation number rule wins out. So this is kind of like a hierarchy. Fluorine is going to be the top one. Then you have group 1 or 2. So when we have LiH, the oxidation number of lithium is +1. The oxidation number of hydrogen can't also be +1 because that would sum to a charge of +2. The charge of LiH is not +2, so that is incorrect. Therefore, if the oxidation number of lithium is +1, the oxidation number of hydrogen must be -1 in order to equal out to its charge of 0. So that's why hydrogen will always have a charge of +1 unless it's with a metal, it makes a metal hydride, so group 1 or 2 metal. Oxygen will always have an oxidation number of -2. The only exceptions to this is if we have any combination with something higher on this list that follows Rule 2 of our assigning oxidation numbers. And this would specifically be for peroxides or KO2, something along those lines. But we will rarely see these examples at this level of general chemistry. You'll probably see these more so in general chemistry 2 when we talk about oxidation reduction reactions in terms of electrochemistry. So for what we're doing here, we will always assume that oxygen has a -2 for its oxidation number. Our final group of elements that have reliable oxidation numbers is going to be group 17 with the exception of fluorine. Fluorine is going to be at the top and always have the oxidation number of -1. So group 1, or group 17, our halogens, are always going to have an oxidation number of -1, unless the exceptions are any combination with something higher on this list, okay, that follows our rules for assigning oxidation numbers, so we have some examples there. So like ClF, well, fluorine is higher on the list, so it's going to take precedent of having a -1. Chlorine also can't have a -1 because that would equal to -2, and ClF does not have a charge of -2. Okay, so we can't have that. So what our oxidation numbers would look like is fluorine having a -1 and chlorine having a +1 to cancel out and give a neutral charge. Okay, so those are our exceptions to group 17. Everything in group 17 except fluorine. Fluorine will always have -1. You are going to want to memorize these specific oxidation numbers. If you know these oxidation numbers, then you can find the oxidation numbers of any other element. Okay, so we're going to practice that today. So the first one we're going to practice together is assigning the oxidation numbers of each element in the compound KMnO4. So the first thing you want to do is we want to write KMnO4. Now, I like organization, I like tables, if you couldn't tell by my balancing lesson, okay? Your textbook also does a kind of table way of doing oxidation numbers. I personally find it very useful. So we use circles and squares to denote our individual oxidation numbers and our total contribution to the molecule overall. So we start with circles at the top and squares at the bottom. The circles are going to be the individual oxidation numbers, and the squares are going to be the total contribution. Okay? So, the first thing you want to do is start out with the oxidation numbers you know. Well, K is in group 1, we know group 1 will always have an oxidation number of +1. So we know K has +1. So we know its oxidation number is +1. We put it into the circle because that's the individual oxidation number of just one potassium. We don't know manganese. We don't have any rules for manganese, but we do have a rule for oxygen. Oxygen will always have a -2. So that's just for one individual oxygen atom. So we put that in the circle because it's for an individual oxygen. In KMnO4, there are 4 oxygens. So the total contribution of oxygen and its oxidation number to the entire molecule is going to be 2 times 4. So we would get a total contribution of -8. Okay? So potassium, there's only 1, so its total contribution is +1. So now, this is again, like I said, it's similar to Sudoku. We can now fill in the blanks to find the remaining oxidation numbers. We know that this molecule overall has a charge of 0. So the boxes must add up to the charge. So that's step 2. The number in the boxes must sum to 0. KMnO4 is a neutral compound. So if I have -8 and +1, what does the oxidation number of manganese have to be in order to equal out to 0? It would be +7. +1 + 7, that's +8. -8 is 0. Since there's only one manganese, the individual oxidation number of manganese would be +7. Okay, so you now fill in the boxes in the same, kind of in like a reverse order. Again, very similar to a Sudoku. So if we were asked for the individual oxidation numbers for each element, K would have an oxidation number of +1, manganese would have an oxidation number of +7, and oxygen would have an oxidation number of -2. So we're looking at the oxidation numbers of the individual elements, not its overall contribution to the molecule. So we were only looking at the circles. Okay, let's keep practicing. I realize that I have H2SO4 twice, so what I'm going to do is cancel this one and give us a new example. And that new example is going to be C6H12. So we don't need that one. Okay, so I have our circles and our squares all set up for these. I'm going to do the first few and then you'll pause your video and finish the rest. So what we want to do is, to start these problems, put in our oxidation numbers that we know based off of our rules. Well, we know that hydrogen is always going to be a +1 and oxygen is always going to be a -2. So that's what we would put into the circles. The individual hydrogen atom has a +1 and the individual oxygen atom has a -2. Since there are 4 oxygen atoms, the overall contribution would be -8. So we take that subscript and we multiply it by the individual oxidation number. The same would then go for hydrogen. We would take that 2 and multiply it by +1 because the overall contribution of all hydrogen atoms is +2. H2SO4 overall has a charge of 0. So what does the oxidation number for sulfur have to be in order to have an overall charge of 0, given that the contribution of oxygen is -8 and the contribution from hydrogen is +2? That would be +6. 2 + 6 - 8 is equal to 0. Since there's only one sulfur, that +6 is the oxidation number of sulfur. Okay, Let's do ClO3 together because this one has a charge, and I said the easiest way to show that rule of assigning oxidation numbers with charges is through practice. So we follow our same rules of determining your oxidation numbers of the elements you know first. So we know oxygen is going to have a -2 charge. Since oxygen lies higher on that chart than chlorine, we can't use our typical -1 chlorine rule. We can't use that, okay, because chlorine would have to be a positive. Okay, we have to have both positive and negative oxidation numbers. So the oxygen rule is higher than the chlorine rule. So we take that value of oxygen first. So we have oxygen being -2. There's 3 of them, so that overall contribution is -6. Now, since this atom, or this molecule, has a charge of -1, this has to equal -1. So the boxes, the sum of the boxes has to equal 1. So what charge does the chlorine have to have in order to make this have a -1 charge? That should be -1, sorry. -1. What charge does chlorine have to have, or what oxidation number does chlorine have to match that -1 charge? Chlorine would have to have a +5, because +5 minus 6 equals -1. There's only one chlorine, therefore the chlorine oxidation state is +5. A good way to visualize these two examples in comparison of their total contribution and their individual oxidation number is if we draw out the structure. So the structure of H2SO4 looks generally like this. There's some double bonds here. You don't need to know how to draw this, okay? This comes with significantly more practice, but that's the structure of H2SO4. Each of these individual atoms has an oxidation number, and overall the molecule has to equal 0. So we know that hydrogen has a +1 charge, but because there's 2 of them, we have to account for it twice. For oxygen, they each have a -2. So we have to account for all 4 of those individual atoms in the molecule because they all contribute to the overall charge of -0. Therefore, sulfur has to have a charge or an oxidation number of +6, okay, in order for all of these oxidation numbers to cancel out and we get an overall charge of 0. Okay, so when we say total contribution, we have to multiply it by those subscripts to account for the different atoms that are in the molecules. Okay, if there's multiple of those atoms, we have to account for them multiple times because each individual atom has a specific oxidation number, but if there's more of them, it contributes more. Okay, so when we say total contribution, hopefully seeing the structure and why we have to multiply it makes sense. Okay, so what I want you to do now is try these 4 examples. Just remember to change this one in your lecture notepad to C6H12, okay? So remember to change that, but pause your video and try these examples. For our first example, we have HPO3. So we follow our rules. We know hydrogen and we know oxygen. We know hydrogen is +1 and oxygen is -2. There's 3 of them, so we want to multiply those oxygens. We get -6. Hydrogen, there's only 1, so its total contribution is +1. HPO3 has an overall charge of 0. Therefore, the total contribution from phosphorus has to be +5. And since there's only 1, its individual oxidation number is also +5. Our next example now changes what our oxidation number is going to be for phosphorus, but we're going to follow the same rules. We know oxygen, -2. We know hydrogen, +1. So there's 3 hydrogens, so its total contribution is now +3. And there's 2 oxygens, so its total contribution is now -4. H3PO2 still has a charge of 0. Therefore, the oxidation state of phosphorus is now +1. +3 + 1 - 4 = 0. So now our oxidation number of phosphorus changes to +1. So those rules that we have for individual atoms, they're there because they have reliable oxidation numbers that are usually unchanging. All of the other elements on the periodic table have various numbers of possible oxidation states or possible oxidation numbers depending on what they're paired up with. So that's why we have to do this. We have to use our rules because we have some elements that have specific oxidation numbers, and we have to use those in order to determine our other ones. So we next have SO3. We only know oxygen's rule, that's -2. Its total contribution is -6. Overall, we have a charge of 0, so the total contribution from sulfur should be +6. There's only 1 sulfur, so we have to have an oxidation state of +6. In our last example, this is where we get a little bit trickier, okay? For this one, we still follow our rules. Hydrogen is still going to have an oxidation number of +1. Yes, it's in the second spot, so it's going to look a little funny, but that's okay. So hydrogen has a +1 charge, okay? It's not with a group 1 or 2 metal, so it does not have its exception. There's 12 of them, so its total contribution is +12. Overall, C6H12 has a charge of 0. Okay, so the total contribution from carbon in total is going to be -12. Because there are 6 carbons, we want to find the oxidation state of each carbon individually. Well, if the carbon contribution overall is -12 and there are 6 of them, how do we distribute that -12 charge over all 6 of them? Well, we take 12 and we divide it by 6. So we get a total contribution of -2. So the individual oxidation state of each carbon is -2. There are 6 of them, so overall it contributes a -12. So we're working backwards here. When we went from 12 to 1, okay, we had to multiply when we went from square to circle to square. Now if we want to go from square to circle, we have to divide. So we can write that. Circle to square, multiply by subscript, and square to circle, divide by subscript. Okay, so that one was a little bit tricky. Okay, let's do some more. For these ones, we want to determine the oxidation number for the underlined atoms in the following molecules and ions. So, even though we're only going to identify the underlined atoms, which you may find similar problems in your homework, we still need to find the oxidation numbers of all atoms in the molecule, okay, in order to properly account for their oxidation numbers in contribution to their charge. So for these ones, we're really just finding the oxidation numbers for all of the atoms. So pause your video and try these problems fully independent. Okay, go through each molecule, identify the oxidation numbers of the ones that you know following those rules. The ones that you don't know, we already did KMNO4, so we already have that one done. So see if you can remember how to do that one. Account for your charges on some of these appropriately. Okay, try them independently. I did not give you any circles and squares, but feel free to draw them on your own paper. I'm going to take a second and draw these in for myself, and then we'll come back and practice them together. For our first example, IF7, we're going to follow our fluorine rule. Fluorine will always have an oxidation number of -1. There are 7 of them, so its overall contribution is -7. Since this has a charge overall of 0, iodine must have an oxidation contribution of +7. Therefore, because there's only one iodine, its individual oxidation number is +7. So the oxidation number of iodine is +7. We always want to look at our circles for these types of problems when it says to determine the oxidation number of the individual atom, okay, because we're not looking at its total contribution to the molecule overall, we want to look at its individual oxidation number. Okay, KMNO4 was our first example that we did, where we said we have -2 for oxygen, +1 for potassium. So we have +1 contribution from potassium and -8 contribution for oxygen. Overall, this needs to equal 0, so manganese is +7. So the manganese oxidation state is +7. K2CR2O7. This one's similar to our last one. We know K is +1. We know oxygen is -2. There's 7 oxygens, so that's a total contribution of -14. We have K2, which is a total contribution of 2 from the potassium. Our overall charge is 0, so the overall contribution from chromium has to be +12. When we're going from square to circle, if we have a subscript, we have to divide by that subscript. So we're going to divide +12 by 2 and we get +6. So the the individual oxidation number for chromium is +6 because its overall contribution is +12 and there's 2 chromiums. So we have to distribute that +12 amongst those 2 chromiums. Okay, I'm going to snake around now. I guess I'll go in a serpentine kind of shape. I'll get rid of that little line there so it doesn't confuse us. Antimony and fluorine. So fluorine we know. F is always going to be -1. And there are 6 of them, so its total contribution is -6. This does have a charge, so we want this to equal -1. So antimony's total contribution must be +5. +5 minus 6 is equal to -1. There's only one antimony, so it has to have an oxidation number of +5. Okay, tungsten and oxygen. Well, we know oxygen, -2. There's 4 of them, so -8 total. It has a charge of 2-, so we have to equal 2-. So tungsten must have a contribution of +6, and since there's only one, that is its oxidation number. Our next example is the carbonate ion, CO3 2-. We know oxygen is always going to be -2. There's 3 of them for -6. This has to equal -2. So we need carbon to be +4. There's only 1 carbon, so its oxidation number is +4. We next have platinum and chlorine, and we have 2 examples of those, where the only thing we change is the number of chlorine. Our charge is the same, but our chlorines are different. So platinum and chlorine, we're going to follow our chlorine rule, so group 17 rule, which says that it is -1. Okay, the only time it's not -1 is if it's with anything, a hydrogen, an oxygen, a group 1 or 2, or fluorine. Okay, so chlorine each has -1. Let's do our first one here. There's 4 of them, so that's -4. This has a charge of 2-, so platinum must have a total contribution of +2, meaning its individual oxidation number is +2 since there's only 1. Now let's see how the platinum oxidation number changes when we add 2 extra chlorines on there. So the chlorine contribution in our second example is now -6. We still need this to equal out to 2- or -2. Therefore, the platinum oxidation number must increase to +4 to account for that. So we'd have to balance out those chlorines with a little bit higher oxidation state on the platinum. There's still only 1 platinum, so +4 is its oxidation number. Okay. And our last example, magnesium and nitrogen. Well, we don't know any rules for nitrogen, but we do know a rule for magnesium. It's in group 2. So, if it's in group 2, it has a +2 oxidation state. Since there's 3 of them, its total contribution is +6. Overall, this has a charge of 0, meaning that the contribution from nitrogen must also be -6. There's 2 nitrogens in there, so we have to distribute that -6 amongst them. So its oxidation number is -3. So when we go from square to circle, we divide by our subscript. Okay, those are our oxidation numbers for all of those examples. We've done a lot of examples. If you like Sudoku, you'll love doing this. I love doing Sudoku, and I love doing oxidation numbers. So, because it's just kind of just figuring it out and multiplying, dividing, and everything like that. So, real fun. Okay, so let's apply this now to our redox reactions, where we learned about oxidation and reduction and moving these electrons. Let's apply this to these reactions specifically with metals. Redox reactions with metals are considered displacement reactions. In a displacement reaction, an atom or an ion in a compound is replaced by an atom of another element. We've seen the word displacement or replacement previously. We've seen it as double replacement. These are also referred to as single replacement or single displacement reactions, where we literally just do we just swap one place. Okay, so we do a single replacement, we replace one with another. So, this is when an atom or an ion in a compound is replaced by an atom of another element. So we're back to our zinc and copper example here, where we take zinc and we replace it with copper. Now I have here chloride because in order for copper and zinc to be in solution, it has to be with a counter anion to balance out its charge. So chloride is going to be that anion. We can see from the oxidation numbers of all of these compounds, which we now know how to identify. Okay, zinc goes from a 0 to a +2. So it was oxidized to zinc 2+. And copper went from +2 to 0, meaning it gained electrons and was reduced. So it went from copper 2 plus and was reduced to copper. So we can see that zinc displaces or replaces copper in the chloride salt. So it literally went from copper chloride to zinc chloride. And we can see what's being oxidized and reduced now through the oxidation numbers, because they tell us how that oxidation number is changing based off of the product or reactant. So when a metal is oxidized by an aqueous solution, so in this case, zinc is oxidized by copper chloride, it becomes an aqueous ion, right? It became zinc plus, zinc 2 plus. Redox reactions must have both mass balance and charge balance, which we've looked at a little bit before this when we were introducing the concept. So I have another example here. Chromium solid reacts with nickel 2 plus ions to create chromium 3 plus ions and nickel solid. Chromium is being oxidized. Okay, its oxidation number is going from 0 to 3 plus, meaning it lost electrons. Okay, and nickel 2 plus going to nickel 0 or nickel solid goes from a 2 plus to a 0. So it is gaining electrons. The reason we say that gaining electrons is reduction students oftentimes get confused because they say, well, gaining doesn't mean reducing, right? The two terms kind of affect each other. What's actually being reduced is the oxidation number is reducing. It's getting more negative. It's going from a 2 plus to a 0, right? It's getting smaller. It's reducing. So that's why we give it the term reduction, okay? I know sometimes students get confused by that. They say reduction, oh, we're losing electrons, because they think reduce means loss. It doesn't mean loss. It means gain, because in order for the oxidation number to reduce, we have to gain electrons in order to do that. So just keep that in mind as you're going through and practicing oxidation and reduction reactions. So nickel is being reduced, chromium is being oxidized, so our oxidation half reaction shows that chromium solid is losing electrons. Specifically, it's losing 3 electrons because it turned into a 3 plus cation. Nickel is being reduced, so it's gaining electrons. Specifically, it's gaining 2 electrons and becoming nickel solid. And what we said earlier was the number of electrons that are being given up and accepted, they have to be the same number, because we can't have just a random electron floating around all willy-nilly doing whatever it wants. They have to go somewhere. But from these two equations, one had 3, so chromium gave away 3, but nickel only accepted 2. That's not correct. So before we can add these half reactions, okay, before we add them up to have the overall redox reaction, we have to balance the electrons. And in order to balance the electrons, we have to multiply these two half reactions by some value so that the electrons balance out. So we have to determine the number of electrons that are needed to balance both half reaction equations. So look at these two equations and think of the factor that you would have to multiply each reaction by in order to have balanced electrons. That doesn't need to be the same number, okay? You can multiply the first one by one number and the second one by another, okay, in order to balance out your electrons. So think of how you would do that. We would need to balance this out by multiplying our top equation by 2 and our bottom equation by 3. So as I said, you don't need to multiply them by the same number. You just need to multiply them by a number so that your electrons will balance. By doing that multiplication, our oxidation half reaction becomes 2 chromium goes to 2 chromium 3 plus 6 electrons. And our reduction half reaction turns into 3 nickel ions plus 6 electrons goes to 3 nickel solid. So we can see here that if we were to add these up, or just to add them as is, I would get 2 chromium plus 3 nickel, 2 plus 6 electrons, goes to 2 chromium 3 plus 3 nickel solids, plus 6 electrons. And as we've said in multiple other balanced equations, if they're the same on either side, if we have compounds that are the same on either side, they cancel out. So our electrons would cancel each other out. I'm just going to erase them. And if we look at our two sides, I now have both mass balance, so I have 3 nickels and 3 nickels, 2 chromiums and 2 chromiums, but I also have charge balance. I have 3 times 2 plus, so this side has a charge of 6 plus, right? There's 3 nickel 2 plus ions, so it has a total charge of 6 plus. And on my product side, I have 2 chromiums that have 3 plus ions, so that also has a charge of 6 plus. So not only do I have mass balance, I also have charge balance. And charge balance doesn't mean zeros on either side. It just means the same charge on both sides. Okay, so let's practice this. We want to write the balanced half reactions and the balanced overall redox reaction for the following reactions. For this first one, we're able to predict our products. Our second one is a little bit trickier, so I'll give us a little shortcut there. But for our first one, we know that magnesium is going to form a 2 plus ion. That's going to go with the sulfate, right? Because we have copper 2 plus, SO4 2 minus. We're just going to swap out our cations. Our metals are going to switch places. So we get copper solid plus MgSO4, right? We know magnesium is going to form a 2 plus ion, so this is now Mg 2 plus and SO4 2 minus. SO4 is going to be our spectator ion in this reaction, right? It's not changing. So what we can do is we can write out our oxidation numbers. So we have 0, 2 plus. We can think of the sulfate ion overall as having a 2 minus because the sulfur and the oxygen are staying together, right? And it's also not changing, which is why it's our spectator. Magnesium becomes 2 plus and copper becomes 0. So we can see that magnesium is going from 0 to 2 plus, so it had to lose electrons. So that would be oxidation. So we have magnesium solid goes to magnesium 2 plus aqueous. And then reduction would be copper. See, we went from 2 plus to a 0, so we reduced our oxidation number. We made it more negative. So we went from copper 2 plus, there we go, aqueous, goes to copper solid. Okay, so those are our two half reactions. We now have to balance them with electrons, right? I have a 0 on this side and a 2 plus on that side for my oxidation. Oxidation is the loss of electrons, so one of the products of that reaction is going to be our electrons. So we lost 2 electrons because we have a charge of 2 plus. Copper gained electrons, so in reduction equations, half reactions, the electrons show up as a reactant. So we have 2 electrons as a reactant in our reduction half reactions. So let's move this over just for space purposes. There we go. Okay, now the number of electrons that were transferred from magnesium to copper are the same, so we don't need to multiply these by anything, so we can just add them up and write our full redox reaction as Mg solid plus copper 2 plus goes to magnesium 2 plus copper solid. We know our electrons are going to cancel out, so we don't show them in our reaction. Okay, let's do the next one. For this one, I am going to have to tell you what the products are because copper can have variable charge. So copper, let's say copper turns into copper 2 plus, so we get CuNO3 2 plus silver solid. Okay, so I give you the reaction here. Let me separate it from the first one. Okay, I give you the reaction here, so what I want you to do is pause your video and write out the 2 half reactions, the oxidation and the reduction half reaction. So figure out the oxidation states of all of the molecules here. Keep NO3 as itself. It is going to be our spectator, so it's not going to matter what its oxidation numbers are. They're unchanging. Okay, so figure out your oxidation numbers, see how things are changing in order to help you determine what's being oxidized and what's being reduced, and then write out those half reactions and try balancing them out with electrons. If we look at our oxidation numbers, copper is going from copper 0 to copper 2 plus, and silver is going from +1 to 0. So copper is being oxidized because it is losing electrons, right? It went from 0 to +2. So we have copper solid going to copper 2 plus aqueous. Okay. And then for our reduction, we have silver, that's not an A, silver +1 aqueous turning into silver solid. That's not silver. There we go. Okay. So oxidation is the loss of electrons, so our electrons are going to show up as a product of this reaction. So we lost 2 electrons. In reduction, our electrons are going to show up as a reactant. We only gained 1 electron, so we're just going to put E-. Okay. These can't be added up as is because our number of electrons are unequal, right? I have 2 electrons and 1 electron. So in order to remedy that, we have to multiply just our reduction half reaction by 2 in order to balance out those electrons. So that would give me 2 electrons plus 2 silver goes to 2 silver solids. So when I add these up now, I'm going to get an overall redox reaction where my 2 electrons are going to cancel out. I'll end up getting copper solid plus 2 silver ions goes to copper 2 plus 2 silvers. So that's our overall half reaction. Or sorry, our overall redox reaction, I should say, coming from our 2 half reactions. So we had to multiply our reduction half reaction by a factor of 2 in order to balance out our electrons. Okay, let's keep going. For these next 2 examples, I want you to write out the half reactions for the following reactions and determine what is being oxidized, what is being reduced, and what the oxidizing and reducing agents are. So pause your video and try these 2 equations, writing out the half reactions for both of these. If we look at our oxidation numbers, we have zinc that is 2 plus, and sodium that is 0, chlorine that is -1, turning into zinc that's 0, sodium that is +1, and chlorine that is -1. Chlorine did not change, therefore it's our spectator ion, so we really want to determine what's being oxidized and what's being reduced between zinc and sodium. So our oxidation half reaction is going to be between whatever is losing electrons, right? Oxidation is the loss of electrons. So we went from sodium 0 to sodium 1 plus. Okay, in order to get a +1 charge, we had to lose electrons. So we went from sodium solid, and that turned into sodium +1. In order to have charge balance, I need to put an extra electron on this side. The +1 and the -1 will balance out. Also, because this is an oxidation half reaction, our electron is going to be on our product side, and that is in order to have charge balance. For our reduction half reaction, we see that zinc now is going from zinc 2 plus to zinc 0, so we're reducing our oxidation number from +2 to 0. So we have zinc 2 plus turning into zinc solid. In order to have charge balance, we have our 2 electrons here, and now we're balanced. And if I want to add up these 2 equations, I'd have to multiply my top one by 2 to balance out my electrons. My question only asked me for the half reactions, so if I'm only asked for the half reactions, I do not need to show the balancing of this, of those electrons. So in your ALEKS homework, when you're only asked to find the half reactions, you don't need to balance out your electrons, okay? Because what's going to happen is if I multiply this whole thing by 2, technically the half reaction by itself can be reduced by a factor of 2, right? It can change those coefficients all by dividing by 2. So the half reaction as is balanced. The only time you would have to multiply by that factor of 2 is if I asked for the entire redox reaction. Okay, so just keep your eye on that in your ALEKS homework and on your exam. If it's asking for the half reactions, you don't need to balance the electrons. Okay, so sodium is being oxidized and zinc is being reduced, meaning that sodium is our reducing agent. Whatever is being oxidized is allowing the reduction to happen and is therefore the reducing agent. Zinc is being reduced and is therefore the oxidizing agent. It's accepting the electrons that are being given up in the oxidation reaction. So remember, they're opposites. Whatever's being oxidized is the reducing agent. Whatever's being reduced is the oxidizing agent. For our second reaction here, we have iron going from iron 0 to iron 3+. We have lead going from lead 2+ to lead 0. And nitrate is going from -1 to -1. So it did not change, therefore it's our spectator. So between iron and lead, we have to determine what's being oxidized and what's being reduced. Iron is going from iron 0 to iron 3+ and is therefore losing electrons, therefore it's being oxidized. So we have iron solid going to iron 3+. Okay, and that's aqueous. In order to have charge balance, I have 3 electrons there as well. And also because this is an oxidation half reaction, we see our loss of electrons. The electrons are going to be a product of that reaction. That means that lead is being reduced because we're going from an oxidation number of 2+ to 0. So we have lead 2+ going to lead solid. Okay, we're reducing our oxidation number. In order to have charge balance, I needed 2 electrons on my reactant side. Also, because this is a reducing half reaction, that is going to be a reactant. The electrons are going to be a reactant in order for them to be gained. Okay, if we were asked to find the full redox reaction, balanced redox reaction, we'd have to multiply both of these by 2 and by 3 to balance out their electrons. But again, I did not ask for the full redox reaction, therefore we don't need to balance out the electrons in the individual half reactions. So that means we can just move on to finding our reducing and oxidizing agent. Iron is being oxidized, so it is the reducing agent. And lead is being reduced, therefore it is the oxidizing agent. And remember what I said earlier about identifying reducing and oxidizing agents in ALEKS? It wants the full chemical formula. So for this one, for our most recent example, the reducing agent would really just be iron, whereas the oxidizing agent would be lead nitrate. Okay, so keep that in mind. So here it would be reducing agent is sodium, oxidizing agent would be zinc chloride. Okay, and that's specific for your ALEKS homework and your exams. Okay, so we can quantify other types of reactions as redox reactions. Most reactions are redox reactions because we're changing bonds, we're moving electrons around. If electrons are being moved around, if bonds are being rearranged, it's a redox reaction. So we've seen some of these before. We've seen combination and decomposition reactions before when we first started balancing chemical equations. So a combination reaction is an example of a redox reaction. Because we're going from 2 compounds in this example that are in their elemental state, so they all have oxidation numbers of 0, automatically those oxidation numbers are going to change once bonds are formed. Electrons are being transferred between those reactants and are therefore going to change those oxidation states. The same can be said for decomposition reactions, except it's the opposite. We're going from a compound and these things are breaking up in these examples into their elemental states. So we're breaking bonds, or we're changing how the bonds are arranged. Therefore, we're moving electrons around. Whenever we're moving electrons around, we have a redox reaction, because the definition of a redox reaction is the transfer of electrons between reactants and products. A new type of reaction is called a disproportionation reaction. And this occurs when one element undergoes both oxidation and reduction reactions. And we're going to see this in reactions where one element in a reactant is turned into, is separated into our two separate products. So this is similar to combustion reactions, where oxygen is being put into both carbon dioxide and water. The example I have here is hydrogen peroxide, where oxygen is going both into water and into oxygen gas. So it's being separated from one reactant into two separate products. So its oxidation numbers in both of those products differ. So here, oxygen in the peroxide, this is one of our exceptions to the rule of oxygen. It has an oxidation state of -1, but since it gets split up into both water and oxygen gas, its oxidation state has different contributions for the two different products. So in water, it has an oxidation state of -2, and in oxygen gas, it has an oxidation state of 0. So we see both oxidation and reduction happening to just the hydrogen, or to just the oxygen atom. The hydrogen here we can see is going unchanged. So the hydrogen is our spectator ion in this specific reaction. So disproportionation is when one element undergoes both oxidation and reduction reactions, and we typically see this when an element goes from one reactant and splits into two products, or the other way around, goes from two products or two reactants and combines into one product. And again, a common one that we see that we've learned about is combustion reactions, where the oxygen gas is turning into both carbon dioxide and water. So our last two practice problems just want us to identify the redox reactions as either combination, decomposition, displacement, which is going to be the single displacement, where we just flip around a cation, and or disproportionation. It can be multiple. Okay, so our first one here, we have two reactants turning into one product. We have phosphorus and chlorine turning into phosphorus and chlorine together. So this would be a combination reaction. Okay, we're going from two reactants and combining them into one product. Next up, we have NO turning into nitrogen gas and oxygen gas. Since we're going from one reactant into two products, this is indicative of a decomposition reaction. In our next example, we have chlorine mixing with potassium iodide, creating potassium chloride and iodine. So we can see here that we just swapped out the chlorine and the iodine. They just swapped places. If they're switching places, this is going to be a single displacement reaction. And finally, we have HNO2 turning into HNO3 plus water plus NO. So we have one reactant turning into three products, so that's automatically a decomposition reaction. But we can see that the hydrogen is going into both HNO3 and H2O, and that the oxygen is going into the HNO3, the H2O, and the NO. So we also have a disproportionation. I'm not going to be able to write that whole thing. Okay, disproportionation. I won't finish it. My terrible spelling skills. So we have both a decomposition reaction, because the decomposition is, the definition is going from one reactant into two or more products, which we did here. And then we have disproportionation because the hydrogen is being split up into 2 products and the oxygen is being split up into 3 products. For our last 4 examples, what I want you to do is try these 4 independently, identifying them as either combination, decomposition, single displacement, or disproportionation. Keep in mind they can be multiple. Our first example was the example we gave for disproportionation. Okay, so this is first a disproportionation. Okay, but it's also a decomposition. Because the oxygen is going both into the water and into the oxygen gas. Our second example is going to be our single displacement. Because the manganese and the silver are switching places and the nitrate is doing nothing. So they're swapping places and displacing each other. Our second to last example is a decomposition, but not a disproportionation, because we're going from one reactant and turning it into 2 products, but neither of those elements are being split up into 2 or more products. So we just have a decomposition. And finally, we have H2 turning it and reacting with Br2, turning into HBr, and this is a classic combination reaction. So that wraps up our second lesson of chapter 9. Move on to complete your ALEKS homework before moving on to your next lesson.